examples. So using the MATLAB and Simulink environments. Of course, if you are not familiar with these tools that are normally used in our universities, you can, of course, you can try to just sharing. So you can try to, I don't know, learn, if you have time, some more details on these facilities that are freely available here. And or, of course, there are some other options, such as far as I know, there are some students that are able to implement many tools in Python, which is a very common now programming language that has the same, almost the same features of the MATLAB. But later we will see some examples, as I said. So we'll try to, according to lecture 5, to make some remarks on system identification, and then we will see two examples of recursive online estimation methods, as we saw in the last lecture, and then an example of the system identification toolbox. So I'm starting with this lecture 6, which is just concluding and summarizing the main topics of our lecture. Of course, this cannot be exhaustive, the lectures that are considering here, because there are some perhaps specific topics that should be addressed, but the aim of these courses is to provide an overview of some important issues, especially for those of you who are not familiar on specific topics, and then you should be able to investigate by yourself after, of course, the lectures, which are the most important issues that perhaps can be of interest for your PhD studies. So this is the main objective of this lecture. That, of course, is impossible to provide a complete overview on everything, because it would require many hours. But so I think is a good trade-off between providing specific topics and give you some driving directions where you can find your motivations and also your specific needs, especially depending on your application and research areas. So let's try to conclude some aspects on system identification. So as far as now, we are in the framework of linear systems. So we saw in the previous lectures an introduction and overview on system identification. Then we we gave attention mainly to non-recursive, so offline, especially to the least square, classic, let's say it's called classical least square approach. And then we examined the recursive. It represents an alternative to classical least square, especially in system identification or adaptive systems. So normally, online identification methods are exploited for the design of adaptive systems or adaptive control. We will have an example later on a simple, we will see, because it requires some knowledge, for example, on the PID controller. So perhaps I will go ahead with recalling some aspects on control, and then perhaps we come back to the adaptive design of PID controller. So as you may remember, the identification procedure consists of an iterative and procedure which consists of different steps. The first one is the experiment design. An important point, as we mentioned earlier, is to choose the input signal. Because you know that the input signal, if you remember, we said that the input signal needs to be generated in order to obtain data which are maximally informative with respect to the unknown contents of your process, because this approach assumes that you are working with an almost black box system. Another problem is to reduce, so also the input has to be selected in order to reduce the influence of the noise. Is another important point, and as you remember, it means that perhaps you need to increase the power of your input in order to counteract for the effect of the noise. Unfortunately, as you increase the size of your input, this can, for example, lead to some problems, because if the system is nonlinear, so you can modify the structure of your system. So it means that you are modifying also the behavior in order to reduce the effect of the noise, but at the same time you are changing also perhaps the operating point of your system. So the selection of the input needs to be selected very carefully. So when you have the data, now you need to choose the model structure. And normally you can, for example, use a priori knowledge of your system, and in some cases also engineering intuition or the knowledge of an expert. This is a difficult step. Then when you have fixed your model structure, so model structure means that you selected, for example, an ARX model, Boxe-Jenkins output error, or Armax. Or it depends, if you remember, on your application. So you can go to the problem of the parameter estimation. So it means that you need to determine the best model, of course, according to the family of your model structure. So it means, for example, the simplest way is to find the unknown vector theta according, for example, to the least square method. Another important point is the model validation. Model validation means that you need to understand if your model is good enough according to the purpose of your model. So of course, good is something that depends on you, only on you, is subjective, and again depends on the purpose of your model. So it's very important to have this aspect clear. So as a picture that we have already seen, so starting the experiment in the data design and the data collection, then we can enter in the identification procedure. So we didn't mention today, but the identification can require, for example, some data preprocessing, for example, to clear, let's say, the data. And then the parameter estimation, model validation, as you can see here, a possible a priori process information can enter at the level of the experimental design, the identification, and the model validation. So at the end, you need to determine if your model is okay. So yes, so you conclude your procedure, but if not, so you may come back to your initial steps. So again, performing the worst case that you need, for example, to acquire again the data, or the simplest one is the, for example, change the model and then to re-estimate the parameters. So in particular, we talk about the in the experiment design, the choice of the input signal. Another important point is the choice of the sampling period. As we mentioned, a very simple way to select the sampling period is to take the settling time, which is a very simple index that you can acquire, because the settling time means that you excite your process with a step, and then from the output you can, for example, this is the output, and then according to the when the response is in steady state, you can evaluate your settling time TA, which is a parameter that can be very easily estimated in the time domain. So it's very simple. You don't need any acquirement, any frequency tool. So the settling time T and the sampling period is very simply equal to the settling time divided. So the smallest choice is settling time divided by 100. So this is a very simple and rough selection of your sampling period. Another important point is what are the signals that you need to measure. Of course, it depends on your choice, on the selection of your system. It depends also on the inputs, and the outputs is something that so perhaps can be enhanced by the knowledge of an expert, of an operator. Also, another point is that how many data are needed. Normally, for this number is defined as n, and normally for linear identification, this number is about, let's say, less than. So the order of magnitude is less than, let's say, 1,000, several thousand. So no more than several thousand. There are also, during the experiment, there are some problems. For example, if there is a feedback in the data, is an important point. In fact, if there is a feedback, so if the system that you are identifying contains some feedback, so perhaps the procedures that we are examining is not the best one. So you need to consider some specific identification schemes for closed loop system, which are different from the methodologies that we examine here. For example, you can check if the system is linear. So it means that by changing the input, you have a consistent change of the output. Also, some tests for time invariance in order to understand if the properties of the system are the same during the time. Something aspect that needs to be considered. So the choice of the input signal. So signal amplitude is something that we already mentioned. So the signal amplitude needs to be sufficiently small in order to remain in the linear region of the system, but on the other hand, on the other side, should be sufficiently large to ensure good excitation and also in order to have a good signal, if you remember, signal to noise ratio. So it means that the level of the input signal needs to be enough to counteract the effect of the noise. Another important point is the frequency contents of your signal. So the inputs should have most of its energy in the interesting frequency region. So again, it depends on the application. As we remarked in the last lecture, remember the persistently excitation conditions. This is required normally, of course, is a theoretical consideration, is required to guarantee the consistency and also the good properties, they say the good physical or statistical properties of your estimations. Of course, we can have physical limitations depending on the process that we are considering. For example, in some cases, you cannot inject your own input signal because it's impossible. So it's, for real processes, you cannot decide the input that you can inject into your process. So you need to work with the signals that are automatically generated. So the persistent excitation condition was based, as you remember, to this empirical covariance matrix, and the problem is that we recasted this problem so this matrix, as you remember, was linked to the problem of the existence of the condition of the least square solution. So it's why, of course, assuming that we can generate these covariance matrices for the input by assuming that the number of data go to infinity. So we obtain these covariance matrices, and we can define the persistently exciting condition that, again, is a theoretical condition, of course. Normally, well, in the linear case, if you are assuming, for example, a white noise input, these conditions are always satisfied, but in general, if you have, for example, if you remember some other signals, for example, the step and the impulse signals, so these persistently exciting conditions have limited validity. So normally, the best, if you can apply your input, the white noise is the best. It represents the best choice. Well, also there is another kind of input which is not mentioned here. Is an important input which is represented, for example, by the summation, the superposition of sinusoidal signals is another possible choice. Is something that is used, for example, when you are considering some civil, some application in the civil area. So you can feed, you can excite your process with some signals which are obtained by a summation of sinusoidal signals, so with different frequencies. This is another possible choice of your input, something which is not mentioned here, but it could be a good choice. So another important issue is the determination of the model structure. So of course, we are considering linear systems, and also another application area is, we limit our considerations to dynamic system, because as we already mentioned, almost the let's say 99% of the processes have dynamic properties. So according to determination of the model structure, we need to consider the algorithm complexity, because if you remember, the more accurate solution is obtained by a complex algorithm. So this means that perhaps you are increasing the computational time and the power, because the computational time implies that you are using more power. Of course, again, it depends on the application. So depending on your conditions, especially, for example, on the hardware that you are using for your application, this can lead to select simpler or more sophisticated models. So it depends. Again, I cannot say in general which is the best one, but it depends again on your application area. So we say that the first approach was with static models. So static model means you are considering what we call finite impulse response model, FIR. FIR is a very simple model which is represented by in compact form in this way. So it means that the output U is simply a moving average. So in general is something like this, B1 multiplied by U t minus 1 plus Bn U t minus n. So where now theta contains the vector b1, b2, bn, and phi is, if you remember, the regressor vector contains the delayed, in this case, delayed only inputs, because it's the input. And in this case, which is also the simplest one when we are considering the properties of your solutions, phi is deterministic because normally U is deterministic, and it does not depend on the old values of Y. Well, in some cases, you can have a phi which contains also the time variable, because you can consider a time varying system, which is not our case. When you consider the most general case of dynamic models, so in general, you obtain this model. So the deterministic part is represented by a polynomial, which is called, or a transfer function, which is called G, and the stochastic part is described by a transfer function of which is called H, multiplied by a vector, or in this case a signal, which is so is U is deterministic input, E is the stochastic output. Input. It represents the disturbance. Normally is defined as the equation error, which is in general modeled by white process with a stochastic process. So in this case, if you represent, so this is the representation in the frequency domain, and this is the representation as a difference equation. So feed in this case depends on the old values also on y. So if you remember, we just mentioned this problem, but in this case, we can use the same results of the deterministic case if we are assuming that the process E is white and the number of samples tends to infinity. We considered 4 families of models. Possible typical models, of course, the FIR are static models, but in general, we have also, which is not included here, but the most general one is the class of models which are called Box and Jenkins, from the name of their developers. The limitation of this model is that these models have a certain dynamic range, and they are valid around what we call a particular working point of the system, because we are assuming that the system is linear, and so the validity of our models is limited to these prototypes. We considered also the different identification methods, in particular what we called the first one, which is the simplest one, is the non-parametric method. So non-parametric methods refer to the case of that models which are represented not really by mathematical models, mathematical descriptions, but normally are represented as with the graphs or plots. For example, the case of the transient response, the frequency response, and so you know that normally you have a graph for your Bode plots or the frequent or the step or impulse response. Why we are using these models or these descriptions? Because they give you some basic information about the system. For example, that time, the time delays, the main delays. So they are also can use for the validation. From one hand we have the non-parametric methods, from the other hand we have the parametric models. As we saw, they are these models, so parametric because the models depend on parameters theta. And in this case, we consider the least square approaches. Not really, we just mentioned the instrumental variable method. Instrumental variable method, which is indicated as IVM. IVM is it represents a modification of the least square approach. So it's something that in general can be applied also to the case of to more complex models. And but the best one is the prediction error method, PEM. PEM is more accurate, so it means that normally it provides more accurate estimations for your parameters, but on the other hand is mathematically more complicated, because it's more the algorithmic complexity is more is heavier, is more important. So This is the approach. And the other consideration should be devoted to the case of online or offline methodologies. We saw that normally most of the cases are offline. The online refers, for example, to the simplest methodology using the least square approach, but is something that needs to be carefully investigated and considering, depending again on your application. So I just want to revise the method. So the simplest one is the least square approach, is an offline method. So you have the system in this form. If you rewrite it as a matrix equation, where V is a disturbance, you can obtain the estimate. So the solution can be obtained in closed form. Of course, we also examined some details of our identification approach. So it means that this approach was obtained by defining the problem of finding the solution which minimizes what we call the equation error. We have, as you remember, the regressor vector, the unknown vector. And so the least square method requires the computation of these. So the solution is obtained by solving the problem of finding the minimum of this cost function, V. And the solution is derived, so by solving this problem. And we obtained this algorithm, which is very simple. We saw that the estimate for a final value of the data is leads to consistent estimates with an accuracy which depends on the noise affecting the data. And so for the dynamic case, we saw that we can obtain the same solution, especially if the noise affecting the data is a white noise, and we obtain also so consistent estimates when the number of data tends to infinity. So we have the accuracy of our solution is directly affected by the noise. Concerning the online identification approach, we examined, which is used in, for example, in adaptive signal processing, tracking time-varying parameters, and especially in fault diagnosis. Most of the methods can be converted into online approaches. Well, perhaps the most complex is the prediction error method, because it represents an approximate solution to the estimation of the parameters, but is also the most accurate. And the online method covered is represented by recursive least square, which is also the simplest one. And we saw briefly, we didn't show this solution, that the solution provided by the recursive least square was represented by an adaptive algorithm. So we have the adaptation law, which is represented by the correction of the solution modified by two factors. The first one represents the model reality mismatch, which is represented by this equation, and the second factor depends on two other terms. The effect of the, let's say, is the joint effect of the noise and the model accuracy, and here we have the effect on the of the input. And we also briefly examined the case of the weighted least square. So weighted least square means that we are introducing a matrix that, and also a factor that allowing to forget the oldest data. This allowed to track for time varying parameters, so it's quite important, this approach. The model validation is another important step. So as is indicated here, a model is of no use unless it's validated. So it's important. So normally we will see some example when I will show you the system identification toolbox. Normally you are comparing in order to understand if your system is off, or if your model is able to describe your real data. Normally you make a comparison between the simulation, so the prediction, and the real data, and then you can compare the frequency response of your models with respect to the spectral analysis performed in your system. And you can also perform some statistical tests. So we didn't examine these approaches because they require some extra time, but it's something that normally is used in your methods. So in order to conclude this summary, system identification represents a powerful technique to provide, to give you a model of your unknown system. In principle, it can be applied to all possible disciplines of science and engineering folks. Well, one important software that you can use for system identification is represented by the system identification toolbox developed in MATLAB. We will see it later. And I provided in my reference some, there is a very nice textbook written by Leonard Leung. Is a professor who developed also the system identification toolbox, which later, I think it was at the end of the 90s, it was included as a commercial toolbox in the system, in the software. And then there are, for those of you who are familiar with this kind of events, we have some workshop or conferences or symposia which are proposed and also proposed by the International Federation of Automatic Control, and there is a specific event which is called SID, System Identification Workshop or Conference event. So it's very specific with this to system identification, to this system identification framework. So, if anybody of you is interested in working on these specific topics of system identification, perhaps is going to attend this kind of events. So this concludes the summary of our system identification approaches.